Okay, good morning, everybody. Welcome to Math 365 PDE. Yeah. I'm technologically challenged today. I didn't bring my bag of tech with me, so I had to rush to ITS at like 8:50 and get some spare camera, but that means I'm without the good microphone. So I'll have to kind of talk by the computer as much as I can for this lesson, which means we have to talk about this paper again, I guess. I do want to eventually stop talking about it, but there were enough questions from that homework assignment that I thought it would be good to actually, try to clear some things up some more. Therefore, please join the Zoom call if you're in the room with me. Well, if you're not able to because of low battery, then that's okay. And I guess I know social distancing, but if you can also come and look at my screen too, if it comes to it. I'll try to move the computer back and angle it so that it's not like everything is insurmountable. Okay. So forgive me still getting oriented, pulling everything up.
I've seen this before.
So getting ourselves back oriented. So looking at this Wilbraham paper. Yeah, it has to pop up on my screen. Oh, there you go. Sometimes it takes a minute for the notification to come up. So where were we? We had looked at this cosine series or partial sum, right? So this y is what I've been calling yn because it really stops at n. You can really differentiate it and then really do this inductive process to say that the derivative of yn is sine 4nx over 2 cosine x. Use fundamental theorem of calculus to say that therefore y is equal to some constant cn plus 1/2 integral from 0 to x of sine 4nt over cosine t dt. We fix those things. If you wanted to figure out y, the limit of the y's, you could take the limit of this equation, right? And maybe c is the limit of the cn's, and this integral as n goes to infinity is going to be y. Now, if you do that, then for any x, if you do that for most x's, this integral will vanish. You can see that automatically, right? Because, well, actually, you can't. Never mind, you can't really see that automatically because n's going to infinity and sine of x is just doing this oscillation. But after doing some more work, we'll see that for most values, if you just take the limit, the integral will vanish. And we're really not interested in just the pointwise limit, right? We're interested in the behavior as n gets large and looking at these peaks and the Gibbs phenomenon. So there's more work to be done on the paper, as we saw. So that brings us to this page 199. So as we saw last time, you calculate this constant by plugging in, say, x equals 0, so the integral vanishes and you're left with c. And so in the limit, you're getting, 1/4 pi as your constant. So Cn is really like the first n terms of this alternating series, and C is like the sum of this series. And so he then proceeds to say that y is like y minus 4 pi is equal to 1/2 0 to x, 4 in x over cosine x dx. So there's my first quibble. It's not really 1/4 pi. It's really this like Cn constant. But that'll be close to 1/4 pi. So in other words, if I graph the function 1/4 pi plus 1/2 integral from 0 to x sine 4n t cosine t, and I also graph the Fourier partial sum, I think that they won't be the same. I think they'll differ by a constant. And I did that, and I want to show it to you now. So I'll stop the share, and then I'll bring up Desmos, and then I'll start the share again. So I went ahead and did more work on Desmos than I did for the previous class. The first thing I did was, well, I'll show you what I had before. What I had before was something like this. The sine series and the approximation. Of course, the sine series is odd, and so it gives you the odd extension. But in the paper, we're talking about the cosine series. So it's kind of better to then look at the even extension. So the cosine series models this, even extension of the square wave, which I've graphed here. And I figured out Desmos does let you do this summation notation, and it does let you put in a neat little slider to show it. So here is the first 5 terms of the cosine series. You can see that gives phenomena starting to appear. And I also went ahead and graphed what he calls the this integral. So where I just left off in the paper, I won't bring it up again right this second, but we had figured out that this partial sum was equal to this integral, right? With the caveat that this constant isn't actually 4 pi, it's like Cn. So let's graph it. Let's see what the software says. They're not looking quite right, the red line and the green line, because like the number of terms in this series doesn't quite match. Let's see if we can figure. So n equals 3. Let's try n equals 4. There it goes. So it takes Desmos a while to actually. I think it was n equals 3. That was right. Yeah, this. As I learned it as I was doing this, that the server side of this software is not very sophisticated. Even with small numbers, I can really max it out, and it just takes forever. So, like, I'd really like to be able to calculate like 10,000 terms of the cosine series or something, but can't really do it with these free web-based apps. But now you can see exactly what I mean, right? Because the green line is the cosine series, and the red line is that integral, and see how it's shifted, showing you that this constant's not quite right. Yeah, Right, because it's the limit as n goes to infinity of the CNs. Right, right, right. And again, I'm not trying to like nitpick this guy from 1850s, but I just want to show you that just because it's written down doesn't mean it's the law. I just want to figure out what exactly is going on. So that's the first thing I figured out. And now let's return back to the paper. So I just showed you the graph of this equation and compared it to the graph of the original y sub n. That's what I was doing. And here they just make a u substitution. So write x equals 1/2 pi minus u over 4n. And you get this expression, and then you use trig identities to get down here. And so this is now y equals 1/4 pi minus 1/2 integral from 4n, 1/2 pi minus x, all the way up to 2n pi. Sine u divided by sine u over 4n times 1 over 4n. And so this is a new expression for y sub n. Why do you need a new expression for y sub n? Because from the original one, it's not clear at all what happens as n goes to infinity. The convergence or divergence behavior is not clear. But when you do this substitution, things start to become more clear. So you get this integral. And speaking about the Gibbs phenomenon, so speaking about those peaks, right? So when you choose x, close to, like for a fixed n, when you choose x, close to pi over 2, like x equals pi over 2 minus 1 over 4n. And then, you can imagine now letting n get bigger and bigger, and so x still being equal to pi over 2 minus 1 over 4n, your x value would sort of creep closer and closer to pi over 2, n's getting bigger. So you've chosen an x value that's sort of like close to the Gibbs phenomenon peak, and you want to know like whether there's a peak or not, right? You want to know whether like as n gets large, does the peak sort of slide down and go to pi over 4, or does the peak persist? And so you're looking at sine u over 4n times 4n. So clearly the integrand here depends on n, right? Because it's sine u over 4n times 4n. But what's the behavior of this integrand? That's the question that Wilbraham's now asking. And I want to go I want to switch back to Desmos, because I also was able to graph this. To switch back to Desmos. And I have to do all of this kind of like one at a time because the server gets overloaded and it takes like 5 minutes to do anything. So I'm actually gonna now suppress the red line. So what's being shown to you now is just like first 5 non-zero terms of, or first 6 non-zero terms of the cosine approximation. You see this next integral. I actually just straight up typed it in. I was amazed that it let me do this, and it also let me put in a slider so that I could choose my n. But Desmos, I guess the way it works is all these sliders are like global variables, so you have to choose a different letter for each one. So I chose L instead of N for this equation. I let it slide from 0 to 100, but I'll start with like L equals 2, and I'll show you this graph. So there it is. And this is, again, supposed to be equal to the cosine series with the caveat that it's like shifted up. So let's bump it up to n equals 3, or like L equals 3. And there you go. So that like the U substitution was legitimate, right? And so when I'm talking about taking an x value close to pi over 2, then like here's pi over 2, right? You can see the jump discontinuity. And you don't want to, like if you get too far over here, you're not going to be close to the blue line, right? So you're kind of wanting to pick x values that are going to be close to the Gibbs bump, because you're actually trying to detect this. And you're actually trying to detect if an increase in n is going to make this bump like go down, or if the bump just like stays, you know, and shifts over. And here you can see the integrand sine u over 4L times 4L. It definitely depends on L. So you might ask yourself, like, how does this behave as L gets large? And so maybe I can do this without referring back to the paper. The next step that Wilbraham does is he says, look, if you are in a very small neighborhood of pi over 2, which I'm kind of, you know, mousing over right now. If you're in a very small neighborhood of pi over 2, regardless of what n is, right? You let n get bigger, and then these functions will change and become better and better approximations, whatever. But if you're in a small neighborhood in the domain of pi over 2, then it should be the case that sine of x is close to x. And therefore, it should be the case that I can replace sine of u over 4L with u over 4L. Then the 4L's drop out, and you're left with sine u over u. You're left with this integral here that I'll show you in a moment. And when I was an undergraduate, and people said things like this to me, what's the very soft-spoken way of saying like you're upset or you're infuriated? I wasn't infuriated, but I thought it was a bunch of garbage. I thought it was a garbage argument, because I said, oh, okay. So if sine x can be replaced with x, do it on the numerator too. And then you're left with the integrand is equal to 1. So, you know, like let's carry your garbage argument to its conclusion. And so what I was getting at, of course, without necessarily having the mathematical tools to figure it out, is when you approximate something by something else, you also need to understand like how close the approximation is to what you started with. In other words, you need to understand like a bound on the error of that approximation. And this is not an analysis class, so we're not going to investigate that. We're not going to develop the mathematical tools to figure that out precisely. But what I can at least do for you is a visualization. I can show you the one integral and compare it to the other integral. And that was the idea for the homework assignment. You know, I said, well, I just wanted you to plug in a couple different values into the two integrals. But I was having you increase n as you were doing it. And so now, since I'm really interested in comparing these two approximations, I'll actually take away my cosine series. So now the black line is the thing that was equal to the cosine series except shifted up by a constant. And now the one that I'm about to show to you, but that's up there at m equals 70, so I should scale that back down to, here I had L equals 3, so I'll pick m equals 3. And this is the approximation, and you should expect it to be pretty good when you're close to pi over 2, and then you should expect that as you move away from pi over 2, it'll be not as good. So let's look at it. Here it is, it's the red line. And see, that's exactly what's happening. So when you're close to pi over 2, the red and the black lines are very close together. And then as you move away, they're kind of diverging. And then as you move away even farther, you're now truly seeing the difference between having the sine function there and not, because there's just, right, here is like the garbage zone where don't even think about it. But here you can zoom in to kind of see the difference. And already you can see Desmos is having a little bit of trouble, drawing everything. But the error between the two peaks is like on the scale of a tenth, right? This is like 2/10.
So the red line is an approximation of the black, which is an approximation of the sun.
Yeah, so the formulas are given on the left-hand side. The red line is this integral formula where the integrand was sine u over u. That is an approximation of the black line. The black line is a really good approximation of the Fourier cosine partial sum. The only difference between the black line and the Fourier partial sum is it's shifted up by a little bit of a constant. And that shift will just uniformly disappear as n gets large. That's sort of guaranteed, because we've got a good handle on that constant Cn, just the first n terms of this expansion for pi over 4. But the thing that would maybe make me uncomfortable as a young student is just taking this complicated integrand and just replacing it with sine u over u, which is also a complicated integrand. Bill pointed out to me after class, like I don't think you can do sine u over u like with elementary methods. And yeah, he said that he could probably do it with a contour integral, and that this might be an advertisement for, like, if you want to take complex analysis at some point, you could see like a technique to do that. And that got me interested. And what I did was I went to my good friend. You know what I'm going to say? I went to my good friend, the internet, and learned that you can do this with Laplace transforms. And I actually worked it out, and I may show that to you if we have time, because you can do it with 364 with the class you've already had. Okay, right. So let's play. So let's take n to be a little bit bigger. So my sliders are L and M. So L is for the black line. So take L to 6 and take M to 6. And look, they're getting even closer. So as n increases, as you add more terms, these integrals appear to be getting closer and closer, right? With L and M equal to 3, they were off by on the scale of a tenth, and here it's more like the scale of 100th. So there's 2 100ths for one of these big squares. So it looks like you're, I don't know, just one of the small squares. So 2/5 of 2 100ths is like the scale for that. Zoom out a little bit. Yeah, I can't bump it up too much because the Desmos can't really draw that well to do the numeric computation. But what maybe all three of you were having issues with in your homework is as you were bumping up n, you're also changing your x value, right? And that was maybe causing some issues. But I hope this proves to you, like I'm just taking the functions and graphing them, that they're getting quite close. So what's the benefit of having this approximation? It's simpler, and the dependency on n in the integrand just left, which is kind of great, because like the whole point is like we didn't really understand how this depended on L. And as long as we stay in this neighborhood, as long as we stay in Mr. Rogers' neighborhood near pi over 2, we're in the regime where you really can very well approximate one with the other. And if the Gibbs phenomenon exists for this function, it'll exist for the other one. I think we're kind of convinced by that, by like how close these lines are. So then comes the idea of actually executing the homework assignment. And so I decided to try to do it too, and that's where like all the rest of this stuff is like coming from. So here I picked, and let me take away the graphs so I can do the sliders, and I'll just get to the single numeric integration. So here I picked x equals pi over 2 minus 1 over 4n, which turns that lower limit into 1. And one of you pointed out to me that Desmos was having some trouble. So what was the trouble? Like if you take, was this what you were saying, Pylon said, if you take like integral from 0 to infinity of sine u over u du, was that it? Well, this says it's undefined, which isn't exactly true. It's equal to pi over 2. And if I take, right, 1 to infinity, because my original question said, actually take 1 to infinity, because what Wilbraham writes is he writes 1 to infinity, but that's not correct. So actually, let me back up and show you that. Let me show you this paper to make sure I'm being sort of clear and fair to the author. So here he's making the substitution, replacing y equals 1/4 pi minus 1/2. Right, and he says 4n times 1/2 pi minus x to infinity. And so what are the mistakes? We've talked about how this 1/4 pi is really not 1/4 pi, it's like constant Cn. It's not a big deal. This infinity isn't really infinity. It's 2 pi n. Like if you, and he's even written it here. I think that's his mindset. But then the problem with that is that, I mean, he's like having his cake and eating it too, because like, because as n goes to infinity, I I guess like my quibble with that is like he's still got sine u over u, like in the integrand. And he's doing a change of variable that also depends on n, right? So he's saying x equals 1/2 pi minus u over 4n. So fix x and u, or like whatever, and let n go to infinity. You're always left with x equals 1/2 pi, right? So you can't literally go to infinity here. That's my point. Or else you don't really have a change of variables. So I think it's not really proper to just change this upper limit to infinity. I think you really want to keep it like 2 pi n. Well, sine of 2 pi n is just going to be 0, but here I'm just talking about here I'm just talking about the limits on the domain. Just going from the lower limit to the upper limit of 2 pi n, which he knows because he correctly wrote here. And realistically, it's probably not going to make that much of a difference either. And he's also telling you he's doing approximation. So it's kind of fine, but whatever. That's why I wrote infinity in the original problem. But if you then plug that in to Desmos, then you're going to have a bad time because you try to calculate like 1 to infinity, sine u over u. So this is with the particular value that x is equal to pi over 2 minus 1 over 4n, then you'll be told that the answer is 0. So that's worse than saying it's undefined because it's straight up giving you a false answer. So I would like to show you how do you calculate integral from 1 to infinity of sine u over u. Do you use Wolfram alpha?
Yeah.
Did it work?
Same thing as Wilbraham.
What does it give you?
I don't know.
Well, so let's take Wolfram alpha. So the student suggestion was, what about the other thing on the internet that we that we use to do homework? Let me share the screen. I'll pull it up. I'll pull it up. So what about integrate sine u? So integrate sine u over u du from u equals 1 to infinity. Gave me an answer, 1/2 pi minus 2 SI. Okay, well, we'll put a pin in that. We'll come back to it, and we'll see if we can kind of get the same answer. Going back to Desmos, I'll show you my idea. My idea was kind of to say, well, like the computer is having problems with infinity, so maybe it can do 0 to 1. So if I can prove that the integral from 0 to infinity of sine u over u is equal to pi over 2, then the integral from 1 to infinity will be equal to the integral from 0 to infinity minus the integral from 0 to 1. That's what I put in there. It's like pi over 2 minus this. Give me 0.62471, which is what Wolfram alpha gave too, right? So yeah, Wolfram alpha was just a little bit more sophisticated than Desmos, I guess. Check that again. Yeah, so pi over 2 minus 2 SI1, but what this term really is I guess the integral from 0 to 1 of sine u over u, like if that helps you. So I think we've reduced the problem to figuring out the integral from 0 to infinity of sine u over u. So let's try it. Yeah, but actually showing that, not just like not just accepting it. Let's give it a shot. I'm going to try to do it with the Laplace transform. So this is like an opportunity to let you review something from ODE. And I don't have a mic, so I'm going to try not to talk too much while I'm writing. I also don't have the high class chat in other areas. So recall. Recall that the Laplace transform of a function t outputs you a function of s. And what the transform does, it multiplies you by e to the minus st and it integrates from 0 to infinity. This should kind of remind you of the formula for the Fourier coefficient. You know, like instead of multiplying by sine times something, it's e to the minus something, but complex form, you know, like e to the I theta is sine theta plus I cosine theta. So there's kind of a similarity there. So that's the Laplace transform. I need to find a function t that I want to transform, and here it is. So look at that. So that's the insight. So that's the clever thing. And the rest of this is just going to be computing. So you take the Laplace transform of f and then the inverse Laplace transform of the result. And that's going to give you a new way to represent this function. It's going to be kind of amazing. So here's the idea. So we want to just write this function as the inverse Laplace transform of the Laplace transform of f. And see what happens. So let us calculate. And my notes just say calculate, so I'll put them down. So just formally plugging in. So I want to do a couple things. I want to switch the variables of integration. And first I'll notice that the e to the minus st, I can bring that inside the integral with respect to x. Because, you know, e to the minus st is like a constant with respect to x. So I bring that in, and then I'll do a switch of integrals due to Fubini's theorem. Dx dt becomes dt dx. Since this domain is rectangular, the bounds of integration will stay the same. So you saw me execute those two steps at once. I first brought e to the minus st inside the integral sin xt over x. And then I used Fubini's theorem to switch dt and dx. So if you take like some analysis, like there is a hypothesis to check there, but you know, the game we're playing is not nitpicking technical hypotheses at this point. We're trying to find a formula, but these steps are legit. And so finally, I'll notice that I can pull the x out of the integral with respect to t. And why do you care about doing this? Because the inside integral looks to me like the Laplace transform of sine of x. Yeah, sorry, this is kind of hard to see. The two things in boxes are the same. The thing in the larger box I recognize as the Laplace transform of sine of x times t. It's being multiplied by 1 over x, and then being integrated with respect to x. Now there is actually a formula for the Laplace transform of sine of constant times t. And x does play the role of a constant here because you look at the definition. Function f depends on t. Take the Laplace transform and get as an output a function that depends on s. So x, there is a constant that then becomes, you then integrate over x after you do the Laplace transform. So I can just look up the formula for the Laplace transform of sine of constant times t. And obviously I did that before class, so I'll just tell you what it is. So let us continue the calculation up here. And now you get this rather wonderful cancellation. Yeah. So the comment was this looks similar to arctangent. So derivative of arctangent is like 1 over 1 plus x squared. So you need to factor out that 1 over s squared. And so this,
Arctan of X over S.
yeah, is that right? So I guess I put in something like that. So 1 over S times 1 over 1 plus x over s squared. You integrate that, and the antiderivative is arctangent x over s. Go from x equals 0 to x equals infinity. Right, so that infinity is interpreted as a limit. Arctangent of 0 equals 0, and arctangent limits to pi over 2. So this finally gives us a chat comment. Yeah, so that finally gives us pi over 2s. Right.
Wait, how do we get that? Arctan. Just what are the two bounds again?
0 to infinity.
Right, so then the limits there are what?
So arctangent. So arctangent limits to pi over 2 as the argument tends towards infinity.
So the limit as x goes to infinity, arctan of x is pi over 2.
Yeah.
Okay.
And arctangent of 0 is 0. So yeah, we need to inverse the Laplace transform. So Laplace transform and its inverse are linear. So I'm left with searching for the inverse Laplace transform of S.
Isn't that 1 over s?
I don't know. Let's Google it.
No, wouldn't it be the
Oh,
x over s?
yeah, 1 over S. So search with me. What's the inverse Laplace transform?
What is the reverse Laplace transform? 1 over s. one.
That almost seems too good to be true. Let's check and make sure we didn't make a mistake anywhere.
I like that we're checking that we didn't make a mistake when we got the answer.
Well, there's f of t is sine xt over x. So if this is true, it means that this is constant function. Seems kind of weird to me. Would mean that this value is pi over 2 no matter what you plug in. Which maybe that's true because you're just like increasing the, the frequency, but when you're going to infinity anyway, perhaps it doesn't matter.
What's the relationship between this integral and sine u over u? Because this one has an extra constant, right?
So the question was, what's the relationship between capital F of t and sine u over u integral? And that's it. That's the point.
That's it. Was it Canada figure this one?
No, this argument is not due to me. It's super cool. It's a super cool argument. So I thought I would share. But I'm trying to rapidly prepare for class, so I didn't look at anybody else like figure it out. So, but hopefully we got every step. Yeah, looks quite good. Quite good. And well, I mean, don't take my word for it. That's the point of mathematics, right? Every step in sequence, and then you can look and see. Yeah, so I was going to leave this alone, but since Desmos was just straight up giving us the wrong answer, I thought, well, let's actually do this, and it'd be a nice review to show you, help you remember Laplace transforms and kind of see some of the beauty of Laplace transform, right? Because we start with this function, and then the transform and its inverse allows us to understand that this function is just being presented in a way that's more complex than it actually is. It's just that constant. Okay, so thank you, everybody. See you on Friday. Have a great day. Thank you for another fantastic class. PDE.